On behalf of myself, Professor Dr. Salah Lotfy, and the entire team behind this channel, I would like to extend special thanks to a distinguished figure in the nuclear energy field, Professor Dr. Tarek Farouk Nagla. Professor Dr. Tarek Nagla is the former research scientist at the Nuclear Power Plants Authority in Cairo, Egypt. His lifelong dedication to nuclear science and engineering has inspired generations of researchers and professionals. His invaluable scientific contributions to our recent video series on nuclear energy have enriched both our understanding and the content I deliver to you, my valued viewers. The thorium question. For decades, nuclear power has relied on uranium, a rare element forged in ancient stars. But what if there's another way? Enter thorium, named after the Norse god of thunder. Thorium promises great power and complexity, offering a potential path to safer, more sustainable nuclear energy. Unlike uranium, thorium isn't directly fissile, it's fertile. It needs a neutron to start a chain reaction. When thorium absorbs a neutron, it transforms into uranium-233, a fissile material that can sustain a nuclear reaction. This is the heart of the thorium fuel cycle, a process of nuclear alchemy that could change how we power our world. Thorium-232, the only stable isotope, is bombarded with neutrons in a reactor, eventually becoming uranium-233. Uranium-233 can be split, releasing energy and more neutrons, continuing the cycle. Why bother with this complex process? The benefits are compelling. Thorium is 3 to 4 times more abundant than uranium and could power civilization for millennia. Its waste is potentially less hazardous and shorter-lived than traditional nuclear waste. Thorium also offers a different path regarding nuclear weapons proliferation, one that may be inherently safer, but the promise comes with profound challenges. The universe rarely gives up its secrets easily. The journey into thorium is a journey into the fundamental physics of the atomic nucleus. It's a delicate dance of particles and forces, played out on a subatomic stage. The potential is real, but so are the obstacles. Can thorium truly deliver on its promise? The answer lies in the details. To understand thorium's promise, we must confront the shadow of nuclear weapons. The uranium fuel cycle carries well-known proliferation risks. Enrichment technology, used to make reactor fuel, can also produce bomb-grade uranium. Reactors also create plutonium-239, another weapons material, as a byproduct. These dual-use pathways have shaped decades of international safeguards and concern. Thorium's advocates argue its fuel cycle could change this landscape. The key fissile product, uranium-233, can be weaponized, but with complications. The process that creates uranium-233 also produces a contaminant that acts as a built-in security system. This makes thorium's proliferation risk different, but not zero. The story is more complex than it first appears. The thorium cycle's complexity comes from uranium-232, an unwanted byproduct. Produced in tiny amounts, uranium-232's real impact is through its decay chain, which emits intense gamma radiation. This radiation makes uranium-233 from thorium reactors extremely hazardous to handle. Any attempt to steal or weaponize this material would require heavy shielding and remote handling. The gamma rays would quickly deliver a lethal dose to anyone nearby and damage sensitive electronics. This self-protection is a major barrier to proliferation. Unlike uranium-235 or plutonium, uranium-233 contaminated with uranium-232 is far harder to use in weapons. The physics of thorium fuel creates a built-in security tag. It's a fundamental difference from the traditional uranium-plutonium cycle. Nature, in this case, helps guard the gate. Uranium-232's gamma shield is strong, but not unbreakable. The intense radiation comes from decay products, not uranium-232 itself. If uranium-233 is quickly separated, there's a brief window before radiation builds up. A sophisticated state could exploit this window to fabricate a weapon. Reactor design can also influence how much uranium-232 is produced, potentially weakening the shield. While amateurs are deterred, nation-states with advanced nuclear infrastructure could overcome these barriers. The shield raises the bar, but doesn't make proliferation impossible. Physics helps, but can't solve geopolitical problems alone. The challenge is technical, not insurmountable. Vigilance is still required. Physics alone can't guarantee safety. International safeguards are essential. Organizations like the IAEA monitor nuclear materials, ensuring they remain in peaceful hands. Thorium is no exception. All materials and facilities must be safeguarded. The high gamma radiation complicates inspections, requiring remote monitoring and advanced detectors. Yet this radiation also makes illicit activity harder to hide. Effective safeguards depend on transparency, access, and global cooperation. Thorium changes the technical details but not the need for oversight. Trust and verification remain the foundation of non-proliferation. There is no substitute for vigilance. The rules must evolve with the technology. Economics drives energy choices, and thorium offers compelling advantages. Thorium is abundant and widely distributed, reducing supply risks. It eliminates the need for uranium enrichment, cutting costs and complexity. Thorium is often found with rare earths, turning a waste problem into a valuable resource. Thorium reactors could achieve higher fuel efficiency, using more of the fuel and producing less waste. These factors point to a potentially more sustainable and economical nuclear future. But abundance alone isn't enough. The full economic picture is more complicated. Thorium's greatest safety feature is also its biggest engineering challenge. The same gamma radiation that deters proliferation makes fuel fabrication and reprocessing difficult and expensive. Fuel must be handled remotely in shielded facilities, driving up costs. Reprocessing thorium fuel requires new, unproven chemical processes. The high radiation degrades equipment and chemicals, adding complexity. Unlike uranium, thorium lacks established supply chains and industrial experience. Building the necessary infrastructure would require massive investment and government support. Until these hurdles are overcome, thorium's true cost remains uncertain. The economic paradox is real. Innovation is needed to break the cycle. Thorium's economic case is a delicate balance of promise and challenge. Molten salt reactors, MSRs, offer a potential breakthrough, dissolving fuel in liquid salt for continuous operation and online reprocessing. MSRs avoid the need for solid fuel fabrication and could simplify waste management. But molten salts are corrosive, demanding new materials and engineering solutions. The chemistry remains complex, and handling radioactive materials is still a challenge. The MSR concept is promising but unproven at commercial scale. Thorium's viability depends on uranium prices, waste management costs, and climate policy. If uranium becomes scarce or waste costs soar, thorium may become more attractive. The economic equation is dynamic, not fixed. The future depends on innovation and changing global needs. Thorium is neither a miracle cure nor a dead end. It offers a path to abundant, potentially safer nuclear energy, but with real technical and economic hurdles. The vision, a world with plentiful energy, less hazardous waste, and greater barriers to weapons proliferation. The reality, we're not there yet. Progress requires breakthroughs in materials, remote handling, and reactor design. Immense investment and unwavering commitment to safeguards are essential. The obstacles are significant, but so is the potential. Exploring thorium is vital for a sustainable energy future. We must research, build prototypes, and test new ideas, eyes wide open to the challenges. The story of thorium is a reminder. Progress is earned, not given. Only through rigorous science and global cooperation can we realize its promise. The journey continues. Preventing the spread of nuclear weapons is essential for global security. The devastation of 1945 showed the world the stakes of atomic power. Since then, the focus has been on keeping nuclear technology peaceful, mainly for energy, not weapons. The Treaty on the Non-Proliferation of Nuclear Weapons, or NPT, is the main tool for this. Under the NPT, non-nuclear states agree not to pursue weapons, while nuclear states work toward disarmament and share peaceful technology. This system has kept the number of nuclear-armed states lower than once feared. But as we seek cleaner energy, nuclear power's risks must be managed. Uranium-based reactors pose proliferation challenges. Enrichment and plutonium production can be misused. Any future nuclear energy system must address these risks head-on. We need energy sources that are both safe and resistant to misuse. Thorium offers a different path. Its fuel cycle is distinct from uranium and plutonium, with unique proliferation implications. Understanding these differences is crucial as we consider thorium's role in a secure energy future. Can thorium deliver clean energy and strengthen non-proliferation? That's the question. The promise is great, but so are the responsibilities. Thorium itself isn't a fuel, it's a fertile material. In a reactor, thorium-232 absorbs a neutron and transforms through a series of decays into uranium-233. Uranium-233 is the actual fissile fuel in thorium reactors. Unlike uranium, thorium doesn't need enrichment, which is a major proliferation benefit, but uranium-233, like plutonium, can be used in weapons if separated. Any system producing U-233 must be tightly safeguarded. The thorium cycle isn't proliferation-proof. U-233 must be protected from theft or diversion at every stage. However, the process that creates U-233 also produces uranium-232. U-232 isn't useful as fuel, but its presence changes everything. It's an unavoidable contaminant in most thorium reactor designs. U-232's decay products emit intense gamma radiation, making U-233 much harder and more dangerous to handle. This built-in deterrent is a key reason thorium is considered more proliferation-resistant. Still, understanding the role of U-232 is essential to evaluating thorium's true security benefits. The presence of U-232 makes the material far less attractive for weapons use. But safeguards and oversight remain critical. Thorium's promise depends on both its technical features and robust international controls. The story of U-233 is complex, but its risks can be managed. Let's compare the main fissile materials, uranium-235, plutonium-239, and uranium-233. Uranium-235 is enriched for most reactors and weapons. Enrichment is the main barrier to misuse. Plutonium-239 is made in reactors and separated by reprocessing. It's toxic and requires complex weapon designs. Uranium-233, bred from thorium, shares traits with both. It's made in reactors and must be chemically separated. Pure U-233 is a potent weapons material, so strict controls are needed. The crucial difference: U-233 from thorium is always contaminated with U-232. U-232's intense radioactivity makes the material extremely hazardous to handle. This contamination is not present in the uranium-235 cycle and only in trace amounts in plutonium. The result: U-233 is far less practical for weapons use. Thorium's built-in radiological barrier is a unique non-proliferation advantage. It raises the technical bar for weaponization. This property sets thorium apart from other nuclear fuel cycles. Uranium-232 is the thorium cycle's secret weapon against proliferation. U-232 decays into isotopes like thallium-208, which emits powerful gamma rays. This radiation penetrates shielding and is lethal to unprotected handlers. Handling U-233 contaminated with U-232 requires remote equipment and heavy shielding, beyond the reach of most groups. The gamma rays also destroy sensitive electronics, making weapon design extremely difficult. Over time, the radiation field grows stronger as decay products build up. Even if stolen, the material becomes more hazardous with each passing day. This ticking clock deters theft and misuse. Unlike highly enriched uranium, U-233 from thorium can't be easily handled or weaponized. The technical barriers are so high that only the most advanced states could even attempt it. For subnational groups, it's essentially out of reach. This passive safety feature is unique to thorium. It's a game changer for nuclear security. U-232 contamination is a powerful deterrent but not foolproof. A determined advanced state could try to minimize U-232 contamination, though it's costly and detectable. Chemical separation of U-233 is still required, and reprocessing is a sensitive step. Facilities handling thorium fuel must be subject to strict international safeguards and monitoring. Inspectors from the IAEA must have full access to ensure no diversion. Physical protection against theft or sabotage is essential. Future technology could make isotope separation easier, so we can't rely on technical barriers alone. A multi-layered defense, technical, institutional, and political, is needed. Safeguards by design should be built into all thorium reactors and facilities. Continuous monitoring and secure accounting are vital. Only by combining passive barriers with active oversight can we ensure thorium's safe use. Thorium's economics are a mix of promise and challenge. Thorium is 3 to 4 times more abundant than uranium, with large deposits worldwide. Its abundance means a secure, low-cost fuel supply. Thorium reactors don't need uranium enrichment, saving significant costs. However, fabricating thorium fuel is more complex and expensive. The real challenge is at the back end. Reprocessing spent fuel is costly due to intense radioactivity. Specialized, remote-operated facilities are required, driving up expenses. The savings from cheap fuel and no enrichment must be weighed against these higher costs. The overall economics depend on reactor design and fuel cycle choices. Thorium's potential is real but not automatic. It requires smart engineering and investment. Thorium is often a byproduct of rare earth mining, so large stockpiles already exist. This means the first wave of thorium reactors could run on existing supplies, minimizing mining costs. Thorium's abundance ensures long-term price stability and energy security. Its energy density is immense. A ton of thorium can replace millions of tons of coal. However, turning thorium into fuel is challenging. Thorium oxide's high melting point complicates fabrication. If recycling U-233, the process must be done remotely due to radioactivity, increasing costs. Different reactor designs, like molten salt reactors, may simplify or complicate fuel fabrication. The economics will depend on which technologies are adopted. Thorium's abundance is a strength, but fuel fabrication remains a hurdle. The back end of the thorium cycle, reprocessing and waste, poses the biggest economic and technical challenges. To fully utilize thorium, spent fuel must be reprocessed to recover U-233. This step is expensive and technically demanding due to intense radioactivity. Specialized shielded facilities are needed, adding major costs. However, thorium produces far fewer long-lived radioactive elements than uranium. Thorium waste is less toxic and decays to safe levels in a few hundred years, not millennia. This could dramatically reduce the cost and complexity of long-term waste disposal. Smaller, simpler repositories may be possible, saving money and easing public concerns. Thorium's waste advantage is both economic and ethical. Managing the back-end well is key to realizing thorium's promise. Thorium offers a compelling mix of security and economic benefits, but it's not a silver bullet. U-232 contamination makes its fissile material unattractive for weapons, but robust safeguards are still essential. Thorium's abundance and lack of enrichment needs could stabilize energy prices and supply. Its waste decays faster and is less hazardous, easing disposal challenges. But higher costs for fuel fabrication and reprocessing must be addressed. Moving forward requires research, prototype reactors, and real-world testing. International cooperation and strong oversight are vital. Thorium's success depends on both technology and global trust. With careful management, thorium could help deliver clean, safe, and secure energy. The path is challenging, but the rewards could be transformative. When it comes to nuclear energy, two questions dominate. Can we prevent weaponization, and can we make it affordable? Non-proliferation is crucial for global security, while cost determines if clean energy is accessible to all. Thorium offers a unique answer to both. Unlike uranium, it's harder to weaponize and is far more abundant. This could mean safer, cheaper, and more sustainable nuclear power. But the story isn't that simple. We need to examine the entire thorium cycle, from mining to waste management, to understand its true potential. In this video, we'll explore why thorium is considered proliferation-resistant, its economic promise, and the real-world hurdles it faces. We'll look at the science, the history, and the economics. By the end, you'll see both the promise and the challenges of making thorium a reality for powering our world. Let's dive in. Thorium's potential has been on scientists' minds since the dawn of nuclear power. In the 1970s, the International Nuclear Fuel Cycle Evaluation, INFCE, studied safer fuel cycles, spotlighting thorium's built-in barriers to weaponization. Unlike uranium cycles that produce weapons-grade plutonium, thorium's process creates uranium-233, mixed with contaminants that make bomb-making far more difficult. These technical hurdles set thorium apart, making it less attractive for weapons use. Still, determined nations could overcome these barriers, so the conversation about safeguards continues. The INFC's work laid the foundation for today's research into safer nuclear options. Thorium isn't immune to risk, but its properties make it a leading candidate for a more secure nuclear future. The quest for safer nuclear energy is ongoing, and thorium remains at the center of that search. At the heart of the thorium cycle is uranium-233, the fuel that powers the reactor. Pure uranium-233 could be weaponized, but in practice it's always contaminated with uranium-232, a game-changing detail. Uranium-232 is an unavoidable byproduct, and its presence makes handling uranium-233 extremely hazardous. The decay of uranium-232 produces intense radiation and heat, damaging electronics and making bomb design unreliable. Even if someone tried to use uranium-233 for weapons, the technical challenges are immense. The risk of pre-detonation and the need for advanced engineering make proliferation far less likely. This built-in barrier is why many experts see thorium as a safer nuclear option. It's not foolproof, but the physics make misuse much harder. The thorium cycle's complexity is its greatest strength against proliferation. It's a technical roadblock that's tough to bypass. The real non-proliferation power of thorium comes from uranium-232's decay products, which emit deadly gamma rays. This intense radiation makes the fuel self-protecting. Handling or stealing it is nearly impossible without heavy shielding and robotics. Any attempt to divert the material would be obvious, as the radiation acts like a beacon for detectors. Over time, the radiation only gets stronger, making the material even more dangerous to handle. This self-protection is a major deterrent, but not an absolute barrier. Advanced nations with specialized facilities could still process it, though at great cost and risk. The technical difficulty and visibility of handling thorium fuel makes secret misuse extremely challenging. While not a magic bullet, uranium-232's radiation is a formidable obstacle for would-be proliferators. It's a natural alarm system built into the fuel cycle. But for true security, we need more than just physics on our side. Let's look at the human safeguards. Even with thorium's natural barriers, robust safeguards are essential. The International Atomic Energy Agency must develop new monitoring tools for thorium reactors and reprocessing plants. High radiation complicates inspections, requiring remote sensors and shielded equipment. Physical security, fences, guards, and surveillance remains critical. Facility design can help, like co-locating reactors and reprocessing to minimize transport risks. Ultimately, a mix of technical solutions and international agreements is needed. Thorium's resistance to proliferation is a strong start, but human oversight is vital. Security must be built in from day one. Thorium's economic appeal starts with its fuel. Unlike uranium, thorium doesn't need enrichment, saving money and energy. But the biggest cost in nuclear power is building the plant itself, and first-of-a-kind thorium reactors will be expensive. Over time, costs could drop as designs are standardized, but the initial investment is steep. Reprocessing spent thorium fuel is also costly and complex, especially due to high radioactivity. The economic case for thorium depends on whether recycling uranium-233 offsets these expenses. Cheaper raw fuel is only part of the equation. Construction, fabrication, and reprocessing costs all add up. The final price tag will depend on technology, scale, and future breakthroughs. Thorium's economics are promising but far from simple. Thorium's abundance is a game changer. It's 3 to 4 times more common than uranium, with major deposits worldwide. This could let more countries produce their own nuclear fuel, boosting energy security. Thorium is often a byproduct of rare earth mining, making it cheap or even free in some cases. If demand rises, this waste could become a valuable resource. Thorium reactors, especially molten salt designs, can use fuel more efficiently than today's uranium reactors. This means a sustainable long-term energy supply for generations. Still, mining, processing, and fuel fabrication costs must be considered. Thorium's best economic case is as part of a broader industrial ecosystem. Turning thorium into usable fuel isn't easy. Making solid thorium fuel pellets is tougher than with uranium, requiring higher temperatures and advanced equipment. The real challenge is handling recycled uranium-233, contaminated with highly radioactive uranium-232. All fabrication must be done remotely in shielded hot cells, driving up costs and complexity. Maintenance is difficult, and mistakes are costly. These hurdles could offset savings from not needing enrichment. That's why many experts favor molten salt reactors, where the fuel is a liquid, not a solid. This design sidesteps many manufacturing challenges, though it brings its own technical issues. Streamlining remote fabrication is key to making solid thorium fuel viable. To maximize thorium's potential, spent fuel must be reprocessed. Standard uranium reprocessing methods don't work well for thorium, requiring new, more complex chemical processes. These processes use highly corrosive chemicals and must be done remotely due to intense radiation. Building and operating such facilities is expensive and technically demanding. The unique waste products from thorium reprocessing also need careful, long-term management. These challenges are major economic and engineering barriers. Still, reprocessing reduces long-lived waste and boosts sustainability. Solving these chemical and waste issues is crucial for thorium's future. The back end of the cycle is just as important as the front. Thorium offers real promise: safer fuel, less proliferation risk, and abundant supply. Its built-in radiation barriers and potential for less long-lived waste make it attractive for a cleaner energy future. But the path forward is tough. High costs, technical hurdles, and complex reprocessing stand in the way. In the short term, thorium power will likely be pricier than today's uranium reactors. Overcoming these obstacles will require major research, innovation, and investment. International cooperation is essential, sharing knowledge, setting standards, and building trust. Scientists and engineers must refine reactor designs, improve fabrication, and develop new safeguards. Governments and industry need to fund demonstration projects and drive down costs. The promise of thorium is global, and so are its challenges. With clear-eyed determination and collaboration, thorium could become a key part of our clean energy mix. The future is uncertain, but the potential is too great to ignore. Nuclear energy is incredibly powerful, harnessing the energy released when we split the atom's nucleus. This process can generate clean electricity, but it also underpins the destructive force of nuclear weapons. The challenge is sharing the benefits of nuclear power while preventing its misuse. The main concern is with fissile materials like certain uranium and plutonium isotopes, which can fuel both reactors and bombs. International agencies like the IAEA work to track and safeguard these materials. Thorium has emerged as a potential alternative to uranium, with properties that may make it less suitable for weapons. Scientists are exploring whether thorium could make non-proliferation efforts easier. It's not a perfect solution, but it could help reduce risks. Understanding thorium's unique features is key to evaluating its role in a safer energy future. Let's explore the science behind this possibility. In the 1970s, global fears about nuclear proliferation led to the International Nuclear Fuel Cycle Evaluation, or INFC. Experts compared fuel cycles, including thorium, to find options less prone to weaponization. The INFCE found thorium's fuel cycle had built-in barriers to weapons use, thanks to its chemistry and physics. While not impossible, making weapons from thorium is much harder, riskier, and more expensive than with uranium. Thorium reactors produce uranium-233, but this comes mixed with highly radioactive byproducts. These byproducts make handling and weaponizing the material extremely hazardous. The technical hurdles act as a strong deterrent. Still, no fuel cycle is completely proliferation-proof. Strong international safeguards and cooperation remain essential. Science helps, but human oversight is the ultimate safety net. The thorium fuel cycle centers on uranium-233, created when thorium absorbs a neutron in a reactor. Uranium-233 is fissile and can, in theory, be used for weapons. However, in practice, it's always contaminated with uranium-232. Uranium-232 forms naturally during reactor operation and can't be avoided. Even in tiny amounts, uranium-232's decay products emit intense gamma radiation. This radiation makes the fuel extremely dangerous to handle and nearly impossible to use for weapons without advanced technology. The contamination is a built-in safety feature, not a flaw. Gamma rays from uranium-232's decay products are highly penetrating and lethal. This makes uranium-233 from thorium reactors a poor choice for weaponization. The result? Thorium fuel is much less attractive for bomb making. That's a major reason it's considered more proliferation resistant. The intense gamma radiation from uranium-232's decay products creates a self-protection effect. Handling this material requires thick shielding and remote-controlled equipment, far beyond the reach of small groups. Anyone attempting to steal or divert thorium-derived fuel would face lethal radiation and easy detection. The material's radiation signature is hard to hide, acting like a built-in alarm system. Gamma rays can also damage the electronics in a nuclear weapon, making the material unreliable for bombs. However, this self-protection isn't instant. Radiation builds up over months after separation. There's a brief window when the material is less hazardous, but exploiting it requires advanced facilities. Technologically advanced states could, in theory, overcome these barriers. Still, for most would-be proliferators, thorium's self-protection is a major obstacle. It's a strong deterrent, but not an absolute guarantee. That's why additional safeguards are still needed. Thorium's physics help, but vigilance is essential. Thorium's radioactive barriers are strong, but not foolproof. International safeguards like those enforced by the IAEA remain critical. One strategy is denaturing, mixing thorium with uranium-238 to complicate weaponization. This makes separating pure uranium-233 much harder. Another risk is the diversion of protactinium-233, an intermediate in the fuel cycle. Robust monitoring is needed to prevent this loophole. The safest approach layers technical barriers, smart reactor design, and strict oversight. The goal make weaponization so difficult and detectable that it's never attempted. The economics of nuclear power are measured by the levelized cost of energy, or LCOE. Major costs include building the plant, ongoing operations, fuel, and waste management. Nuclear plants are expensive to build and require skilled staff and constant maintenance. Fuel costs involve mining, processing, and fabricating nuclear material. Uranium enrichment is energy-intensive and costly. Thorium could offer savings by skipping enrichment. Long-term costs also include storing spent fuel and decommissioning old plants. These responsibilities add unique financial challenges to nuclear energy. All these factors must be considered when comparing nuclear to other energy sources. Thorium is 3 to 4 times more abundant than uranium and widely distributed globally. Its abundance means a more secure, stable, and affordable fuel supply. Natural thorium is almost entirely usable as fuel, unlike uranium, which requires costly enrichment. Thorium reactors can extract more energy from each ton of fuel, increasing efficiency. This higher efficiency means less waste and fewer long-lived radioactive elements. Skipping enrichment and using fuel more completely could lower overall costs. These advantages could make thorium reactors more competitive. However, the full economic picture depends on overcoming technical hurdles. Thorium's promise is real, but not automatic. Thorium's benefits come with manufacturing challenges. Making thorium oxide fuel pellets is harder and more energy-intensive than with uranium. The process requires higher temperatures and specialized equipment. Gamma radiation from uranium-232 contamination means fuel must be handled in shielded, remote-controlled facilities. These hot cells are expensive to build and operate. Transporting and loading thorium fuel is also more complex and costly. The added safety measures increase operating costs. For thorium to be viable, its savings must outweigh these extra expenses. Thorium offers a promising path for cleaner, safer nuclear energy. Its built-in barriers make weaponization much harder, addressing major security concerns. But no technology is perfect. Determined actors with resources could still pose risks. International safeguards and cooperation remain essential. Economically, thorium's abundance and efficiency are big advantages. Yet the costs of handling its radioactive fuel are significant hurdles. Overcoming these challenges will require research, investment, and new supply chains. International collaboration is key to unlocking thorium's potential. Thorium could be a cornerstone of future energy, but only with careful planning and oversight. The journey is complex, but the rewards could be transformative.